Yeah.
Good afternoon, everyone. So to kick us off, we have Alexander Lobbe from Imperial College London, who wants to talk about generative modeling of stochastic parameterizations for fluid dynamics.
Thank you, James, for the introduction. So yeah, this is my presentation about modeling the noise in the stochastic parameterized fluid dynamics system. And I'll be presenting a case study on the rotating shallow water model. And just to quickly mention, so this is part of the project Stewart, the European funded project for stochastic transport in upper ocean dynamics. And so this tries to insert a noise into ocean models and try to recover the loss of scales. And I will say more about it as we go on. And yeah, this is a joint project with Dan Krisan and Wana Lang. Okay, so what is the goal of this work? So the goal of this is we want to learn a generative model for the noise in the stochastically parameterized computational fluid dynamics problem. And we would like to then use the stochastic model to generate ensembles to use in forecasting. So this will hopefully give us a principled way to perturb deterministic fluid PDEs in order to generate more physical ensembles for forecast studies. And so I'll first present the stochastic parameterization that we are using and the associated rotating shallow water system. I'll then quickly introduce the score-based generative modeling via diffusion Schrödinger bridge, which is the algorithm that probably many of you have seen by Arnaud Doucet and collaborators. And then I'll be presenting our ensemble forecast studies and the score that we have estimated using the generative model noise. Okay, so what's the goal of this stochastic parameterization? So the geophysical fluid dynamical models usually include features at many different scales. So they have small waves, and large variations and small variations. And we would like to normally resolve them in numerical studies as accurately as we can. But of course, there's always going to be a limit in terms of computational power that we can afford to simulate them accurately. So we would like to go to a coarser resolution and preserve as many features of the models as we can. But of course, just coarsening the grid usually leads to a loss of accuracy in the model. And we would like to account for this loss of accuracy in the coarse model by adding a stochastic term in the reduced model and hopefully recover some of the features that sort of diverge when you just run a model on a coarse and a fine scale. And of course, if we want to parameterize this model stochastically, then we need to somehow calibrate the covariances of the stochastic term. And because this sometimes is a little bit cryptic, I want to show you a small video just to illustrate what this may look like. So I hope the screen has it's a bit blurry, but on my screen it's maybe a bit better. But anyway, so we have on the left a simulation of a fine run of the PDE. So this is a non-dimensionalized model on a 0,1 by 0,1 square domain. And so on the left, this domain is discretized into 256 by 256 grid cells. And on the right, we have the coarsened domain, which is 32 by 32. The left model is the PDE without any noise run on the fine scale. The middle is the coarsened PDE. So that's a PDE just run on the coarse grid without any noise. And the right one is an ad hoc SPDE where we just use an ad hoc Gaussian noise to illustrate what is happening. And on the bottom, I plotted the normalized power spectral density of the fields that you see on top. So this is for the variable height of the fluid. And you can see here, so the x-axis here is the wave number. And then you can see that the gray line, that's the fine PDE. It includes more scales because it's a finer grid, so it can resolve more fine variations. And then on the coarse grid, of course, it drops because that's where the grid scale is not able to represent the noise anymore. Okay, so let me just run this. So you can see as we run, let's stop maybe here. We have in the fine run, we have a lot of fine scales. You maybe have seen this one lifting up a little bit. So many fine waves are developing in this fine resolution model, which you cannot really see in the coarse PDE because, of course, the grid is not able to represent them. And in the coarsened SPD, you can see it looks pretty much like the coarse PDE, but it's just a little bit perturbed by this Gaussian noise. And as time goes on, this perturbation will be stronger and stronger, and these two will diverge as well. So we can just keep on going. Yeah, so you can see the solutions just diverge there. And what you can also pay attention to is that we are using Gaussian noise here, so it basically uniformly adds some wave numbers to the spectrum. So of course, the SPD spectrum on the coarse grid will have a little bit more variation in the higher wave numbers than the coarse PDE. And you can also see that between the fine PDE and the coarse PDE, also the macroscopic features will start to diverge a little bit. So maybe here we haven't run it for such a long time that it's really obvious. But for example, if you look in the lower left, there's like a huge dark spot here. And this huge dark spot is not here. There's a small one, but not this huge one. So also the macroscopic features here are starting to diverge. And the idea is we want to find a noise for this coarse PDE so that the macroscopic features that are in here are represented here in the coarsened version. So this one should look like a coarsening of this one and not of this one, right? I hope this is kind of clear. And this is the idea of trying to find these noise parametrizations. Right. So to put this a little bit into a bit of mathematical notation, so we think of the geophysical fluid dynamics model, so of the PDE, as being just a PDE with some model operator curly A, and this we call the high resolution model. And we want to replace this by a low resolution model MC. And MC incorporates the effect of the unresolved scales to a stochastic term, which is here, which has a model operator curly M, and is a stochastic integral against the space-time Brownian motion, which includes the covariance scalings psi k in here. And the coarsened model then should solve the SPD given here. So we use the same PDE operator here on the coarser grid, and we add the stochastic term in there. And so in theory, if we want to analyze this model, MF and MC, they live on the same domain. They just live in whatever space you're considering the fluid to be in. But the numerical resolution will be on different grids. The grid for the fine model is obviously finer than that of the coarse. And so now we need to collect data in order to learn the stochastic parametrization. And we need to pick sort of the correct data set to represent the divergences between the different grids. So we partition our time, and then we estimate the vector fields from the difference between the fine scale solution and the coarsened fine scale solution. This is already noted here by M hat. So this is the remainder after removing the coarsening of the high res fields. So that means that's basically all the fine scale variations that you have in your run. And you could take, for example, as the coarsening operator, a low pass filter, which removes all the fast oscillations. And the way that you then obtain the data set for the model will now depend on the choice of the perturbation that you make for your SPDE. So we can think of this time difference here as a discretization of a small Euler step of this stochastic integral. So we need to somehow reverse this model operator. And this reversion obviously depends on what curly M is. We can do this, for example, for additive noise. We can do it also for multiplicative noise, and we can do it for a noise that's called SALT SRSW. So SALT stands for stochastic advection by Lie transport, and this is the one that we will be looking at today. Yeah, for the fluid dynamics people here, this assumes that the psi, the vector fields are divergence free. So yeah, what are the variables? So h denotes the height of the fluid, and then there are sometimes different parametrizations for these variables. So you have your height of the fluid column, then you sometimes have some bottom topography little b, and you can also define the average height of the whole domain by capital H. And then sometimes people write their models in terms of eta, which is the elevation relative to the average fluid height. So on the bottom here, this is how you convert between the variables. So capital H plus eta or little h plus b, both would correspond to the z coordinate of the fluid surface, right? So if you want to know where the surface is, you can either use capital H plus eta, if that's how you parameterize the equations, or little h plus b. Okay, so now the noise that we are using is the so-called SALT noise. So this is one possible way to account for the fast scales or the unresolved components from a deterministic fluid model. And the advantage is that this has been mathematically derived and is physically consistent with the underlying deterministic model. So this was done by our colleague at Imperial, Darrell Holm, in this paper in 2015. And he derived this noise from variational principles. So that means that he used a fluid mechanics framework, a geometrical fluid mechanics framework to derive these equations. And the good thing about them is that they preserve certain invariances that are in the equation. So that they preserve some quantities, not the energy, but an infinite number of other quantities, which I'm not the right person to explain. But okay, if we write the rotating shallow water model in the primitive variables, then the deterministic model would be all the black terms in the equation. And we are adding a stochastic term, which is the sum of these one-dimensional Brownian motions here with these stochastic operators L and A, and this stochastic term in the continuity equation for H. So here the vector fields are divergence free and time independent. And this is how the operators are defined for the stochastic terms. Okay, so now to obtain the data distribution for this type of model, we need to invert this model operator curly M. So curly M would be basically what's in front of the dW here. And because of the divergence-free nature of the psi, it turns out that we only need the continuity equation for this specific SPDE. So the data that we have, we only need to take them from the field for the height variable of this equation in that case. So if we approximate this infinite sum of Brownian motions by a finite sum, then this is what the operator looks like written out. So there's this coarsening operator here of the fine scale run. So this is a coarsening of the height fields. And if we just do the calculations, then it turns out that this variable psi that's in here should be distributed according to the sum of some covariant scalings and then the Brownian motion increments, right? But of course, this is another PDE, so we need to solve this PDE for psi at every time step that we want to collect the data, right? And you can think of the gradient of these psi's that are in here as the psi's that we are actually looking for. So these psi's here, they will represent the velocity perturbations, because excising here, they are two-dimensional, but the data that we have in here, because it comes only from the height variable, is scalar. And because of that relation with the divergence-free vector fields, it turns out that we can represent the divergence-free vector fields as the perpendicular gradient of another scalar function, which is the one that we're studying. Okay. And by now, what you could basically do is, if you know this, you could take all the psi's and do a PCA and just check what your sort of basis functions are. And we've done that in the previous work, but we thought, okay, maybe this model isn't perfect, and maybe the data that we get from the actual fluid is not normally distributed. So we thought, okay, let's go back here and let's just take what we have here, take the data, but remove the assumption that it's distributed according to these Brownian motions here. So we relax this Gaussian assumption, and we make now the answer is that this perturbation has a stochastic representation, which is given still by the model operator, but now with a different noise process. And this noise process we now want to model via a generative model. And so the assumption that remains here, though, is that the distribution of this capital N is stationary, so it doesn't change in time, which may or may not true for the fluids that you're looking at, may or may not be true for the fluids that you're looking at. But in this case, we do it because the generative model will sample from a fixed data distribution. Otherwise, we would just have one sample for each time step. So maybe with one sample, we won't get a good model. So we make this assumption. Okay, and now because the velocity perturbations are thought of as a stream function for the data is thought of as a stream function for the velocity perturbations. That means that the output that we obtain from the generative model will represent the velocity perturbations like this. So you take the perpendicular gradient of the output of the generative model, and this gives you the perturbations U1 tilde and U2 tilde for the velocity in the shallow water model. And just so that it's a little bit more clear, this is how we implemented the salt equations numerically. And this is where the perturbations will enter. So there's this advective velocity here, which gets perturbed by the U tilde. And then there's another term which comes in from the salt noise. And also the continuity equation is perturbed by this. So this is not just adding noise to the equations. This is actually adding it in such a way that it perturbs the transport part of the equation, but it does not introduce an additional forcing into the exterior of the fluid. Okay. One more technical detail. So to do the simulation numerically, it's sometimes difficult to work with fluid dynamics models because everything is very sensitive to the number of grid points that you use and the initial condition and things. So there are a lot of scales that you need to consider. So there are scales for velocity, scales for the length of the domain, and there are also scales for time and for height and so on. And in order to reduce sort of the number of parameters that we have to play with to get a good simulation, we divide by all these scales here, which in fluid dynamics is called non-dimensionalization, to obtain an equation which uses only order 1 variables and has only 2 parameters which are dimension free. One is the Rossby number and one is the Frude number. And so by playing with these 2 parameters here, instead of changing the grid and changing many different things, we can obtain different properties of flow, right? Different flows with different properties. And in our case, we have the Frude number and the Rossby number. So the Rossby number, for example, characterizes the strength of the rotation. And the Frude number characterizes the inertia that you have. So that's the U here versus some external forces. And often these external forces are just gravity. Yeah, so now all the variables that we have are order 1. And so the model that we have in this test has been discretized into 128 by 128 grid cells and uses a time step of 0.02 times dx and preserves the CFL condition. Okay, so we chose a simple initial condition. It's just these two bumps. One is sort of higher and one is lower than the average fluid surface. And so if we run this model for a while, then we just want to verify that we're actually getting the fine scales that we are trying to model. Because if your flow is sort of too nice in a way, then there might not be these fine scale features. And then if you take your model minus the coarsening of the model, you may be left with nothing, and then you have no data. So we don't even need to try to do our things. So here we actually see that we get, for example, these fine scale waves here, which are definitely not resolved on the coarse scale. So we should be fine in obtaining some data that we can then use to train the generative model on. And yeah, this is again for the height field because this is the field that we are using to generate the data. And just for the practitioners, so once we have obtained all the data, we just globally scale it and apply some transformation. In this case, this is an arcsine H transformation, just sort of to spread the pixel values over the whole space, because otherwise this would be really compressed and it would be hard for the model to learn. So this is the final distribution of pixels that we're getting. I have no interpretation for this, so this is just what everything collected together and then what it as a histogram looks like. And here are some of the training images finally. So this is a distribution that we are trying to learn from the generative model. So this is the data distribution. And this is definitely not Gaussian noise. There's some structure in here. So you tend to get these sort of bigger blobs here, and then they're separated by some of these, I don't know, streamlines. But yeah, this is the capital psi. This is the data that we want to match the distribution. Okay, so in the interest of time, because I've already talked for almost half an hour, I will skip this part because it will probably be familiar to most of you. So this is how you do the score-based generative modeling. And just one comment. Now, if you do the score-based generative modeling all by its own, you usually just train a forward pass and a backward pass, and that's it. So you need to be careful with how many steps you're taking and things, so things can be quite sensitive. And the innovation of this paper by Duce and others is that they are using this Schrödinger bridge method on top of the classical score-based diffusion models. So you think of your diffusion measure, the measure on the path, and you want to find the Schrödinger bridge, which means that you want to find the measure in the path, in the space of path measures, which has the marginals of the data distribution at time 0, and the prior distribution, which is usually a simple Gaussian at time n. And if you have that, then you can sample from the reverse time dynamics. And there is a standard solution method for this sort of optimal transport kind of problem, and that is called iterative proportional fitting. So you sort of alternate between two steps. So in the odd steps, you fit it such that the Kullback-Leibler divergence between whatever you're looking for, and the other one is minimal, given that the last step is the prior. And then you take another step given that, and you fix the pi 0 to be the p data. And it turns out that under certain conditions, this iteration will produce exactly what you want. And so in pictures, this picture is taken again from the paper by Duce. This is the normal diffusions that you get, right? You want to transform something into your data distribution, but these might not be perfect, right? So it may be that in the first iteration you transform it, but you've just not noised it for enough. And in the reverse, the same, right? You sample from a Gaussian and it might not take you to your data distribution at all. And with this iterative proportional fitting, you can iterate the whole path here and do what they call here DSP steps in order to train the whole thing. Iteratively to obtain a better sampling in the end. So this makes it a little bit easier to work with the diffusions, in my opinion, and it allows you to reduce sort of the number of steps that you take for the diffusion. Yeah, I'll skip this. Probably you know this. So if you want to fit the backward net, then the loss depends on sampling from the forward net and vice versa. So now we've run this here we're using 30 diffusion steps. We take 10,000 iterations per training step. So that's 10,000 iterations for each of these. And we use only 3 iterations of the iterative proportional fitting. And we use a step size schedule. So step size here refers to the steps in the diffusion, which is linear and takes us from 1/10 to 10 to the -5. And these are the samples that we obtain from the distribution that we wanted to model. And I think it looks quite good. There are some noisy samples in there. So maybe we can tune it a little bit more. But this definitely looks like samples from the distribution that we have here. Right, so you can, for example, if you look at this one, you'll find something similar. Find something similar maybe in here.
Can you quantify that? Because, I mean, I look at those pictures, I often see this kind of thing presented.
Yeah.
And I don't see the same thing you do. I see, of course, can see some large, gaps.
Yeah.
Which is suggestive that you might have something.
Yeah.
But I can't tell, for example, that you have the right variation.
Yeah.
It's a bit, this eyeball norm is quite.
I mean, you can, I see what you're saying, and we definitely want to do this as well. However, it's not necessarily needed that we fit this distribution perfectly, because actually the overall goal, what I mentioned in the beginning, is to generate a good ensemble for the forecast. So it might be that even this imperfect distribution still generates a good ensemble for the forecast. So the sort of the quantifiable metric that we're using to assess the strength of this would not be to use like a FID of this versus the training set, but we actually want to check the forecast metrics if these are improved.
I mean, just to reiterate, I mean, I can see, for example, that several of the samples look quite similar. So that means variation might not be very good, which is exactly the issue that you're facing.
Yeah, this could be. Okay, yeah, but thank you for the comment. And so one thing that we've done, we've compared the samples that we're getting from the generated noise versus a Gaussian distribution. So it seems to be important also for ocean practitioners, oceanographers, to check the distribution of these variations. And these are the variations at different points in space throughout the domain. And we've done here a Kolmogorov-Smirnov test of a Gaussian versus the generated noise. And at none of these tested points here do we obtain something that looks like a Gaussian distribution. So we've definitely fitted something that is non-Gaussian to this, to represent the noise in the model. And so finally, and then I'll finish, we've done a very small forecast study of the generative model noise against the Gaussian noise. So this is for a forecast lead time of 200 time steps. And we've used now 3 different noises. So one is the generative model. And then we have a Gaussian noise, which is Gaussian and with the same distribution at each point in space, right? So it has only diagonal covariance with one parameter on the diagonal, and that's it. And then we have one which may vary on the diagonal, but it's still a diagonal Gaussian, right? So, and all of these standard deviations are adapted so that the standard deviation of the generated noise corresponds to the standard deviation of the Gaussians that we are comparing it against. And we have 3 different scenarios for the initial uncertainty. So when you start your model, you may start all the ensemble members at the same position, which corresponds to the true position that you're also starting your PD on. This would mean that you have 0 standard deviation in the initial ensemble. You've got low initial uncertainty, and this for us is 0.001 standard deviation in the perturbation of the initial value, or high initial uncertainty. And we assess 2 metrics. One is the continuous rank probability score, and one is the root mean square error. And so the continuous rank probability score, it compares something which is a distribution against a truth, which is a Dirac delta distribution, and it just quantifies the distance between the two, basically. And so here are the results. So if we have no initial uncertainty, then so blue is the model from the generative noise, and orange is the Gaussian, which has only one value on the diagonal, and green is the value which has different standard deviations at each point in space, but is still diagonal. And so lower is better for both these scores. And so for the CRPS, we can see that the generative noise is much better if you start it without initial uncertainty. If you add low initial uncertainty, it still kind of does better. It's got some large variations, but overall, I would say it's still a little bit better, especially for the variable height, which may have to do with the fact that the data already comes from the height, so maybe it's adapted a bit better to this. And if you have very high initial uncertainty, that means that the initial uncertainty basically just dominates everything that you do. So now we see them all performing the same, which is also what we expect to see. And a similar picture for the root mean square error. But in root mean square error, we have some oscillations in the generative model, which are pretty strong. But overall, in the height variable, we're still doing better than the Gaussian perturbation. And also, things get destroyed if we have too large of an initial perturbation variance. And so the conclusion is that we can generate an appropriate noise for the subgrid scale effects in fluid dynamics using these generative models. And one may try different versions of generative model. DSB is just one that we chose. And another observation is that the generated noise can actually model the deviations from Gaussianity. And the ensembles that we generate seem to be better suited to do ensemble forecasts than just using Gaussian perturbations of the transport variables. And yeah, the preprint is available. And this will be my talk.